Sai Krishna, studying EC from VVIT in section B, and my roll number is 20BQ1A04C5. Today my topic is quantum mechanics. First we discuss about introduction to quantum mechanics, wave particle duality, de Broglie's hypothesis. Quantum mechanics is a process study of process which occur atomic scale. The word quantum is derived from Latin. Therefore, we study the motion of the objects that come in small bundles called quanta. The tiny bundle that are we are referring electrons traveling around the nucleus. Now we discuss about wave and particle nature. The concept of a particle is very easy to grasp. It has mass and it is located at some definite point. Thus, the particle is specified by mass, velocity, and momentum and energy. The concept of the wave, it is an energy carrier. A wave is specified by the frequency, wavelength, phase or wave velocity, amplitude, and intensity. The wave will transfer energy from one place to another place. Hence, it is appear to difficult to accept conflicting ideas that radiation has dual nature. Radiation is a wave which is spread over space, and also particle which is localized at any space. Radiations including visible light, infrared, X-rays, etc. behave as a waves in experiment based on the interference, diffraction, etc. It is difficult for the two particles to occupy the same position at the time that we conclude that radiation behaves like wave. Planck's quantum theory was successful in explaining black body radiation, Crompton effect, and had clearly established the radiant energy in its interaction with matter behaves as through its consist of corpuscles. Thus, we conclude that radiations behave like a particle. Radiations thus sometimes behave as a wave and sometimes particle. It has wave particle dualism. Hence, it should be remembered that radiation cannot exhibit its particle and wave properties simultaneously. Now, waves and particles. Waves can be superimposed and spread in space and time. Particles cannot pass through each other, they bounce and shatter, localized in space and time. Expression of wavelength of matter wave. Light frequency is associated with a photon energy E. By applying Planck's constant relation, E is equals to hv. The mathematical expression for the wavelength of the matter wave can be derived taking a photon consideration into radiation. According to Einstein, E is equals to mc square. If a photon attains a mass m during motion with velocity c, then we can write h mu is equals to mc square. Since momentum of photon is p is equals to mc, the above equation can be written as h mu is equals to pc is equals to p mu into lambda, because c is equals to mu into lambda. Finally, h lambda is equals to h by p. Lambda minus h by p is equals to h by mv. Some cases are discussed in the following points. If the particle is accelerated to a kinetic energy E suffix k, then we already know kinetic energy is equals to half mv square is equals to 1 by 2 multiply and divide with m is equals to mv square is equals to p square. You already know p is equals to square root of 2m into e suffix k. Now There we can also write de Broglie wavelength lambda is equals to h by square root of 2m e suffix k. If a particle accelerated with electrostatic energy, then kinetic energy is equals to q into v, where v is accelerating potential. Now momentum with p is equals to square root of 2m into qv. Then de Broglie wavelength is lambda is equals to h by square root of 2m q into v. Now when particle is accelerated with help of thermal energy, then kinetic energy is equals to 3 by 2 into kt. Then momentum is also write as square root of 3m kt. Then de Broglie wavelength is equals to lambda is equals to h by square root of 3m kt. When particle is moving with a velocity comparable that of light, then particle no longer remains constant. It will vary according to the following equation. M is equals to m naught by square root of 1 minus mu square by c square, where m is the particle during its motion mass of particle and m naught is the rest mass of particle. V is equals to velocity of particle, c is equals to velocity of light. Hence expression for de Broglie wavelength will be slightly modified as shown in the following. Lambda is equals to h by m into mu h into 1 minus g square by c square by m naught into mu, sorry, v. De Broglie wavelength is associated with electron. Then let us consider electron of rest mass m0 and charge E accelerated by the potential difference V. Then kinetic energy is equals to EV 1 by 2 m v naught square, m naught into v square is equals to EV. Then velocity of electron is equals to square root of 2 2 ev by m naught. This all the de Broglie wavelength is equal to 1 by m naught into v is equals to h into square root of m naught by m naught into square root of 2 ev. Here we also write as lambda is equals to 1 by square root of 2 ev m naught, where h is equals to Planck's constant. It contains the value of 6.652 into 10 power minus 34 joule per second lambda. Now 2 into charge of electron E and V into mass of electron 9.1 into 10 power 31. Finally we get lambda is equals to 12.26 by square root of V Armstrongs. Now we discuss about properties of waves. Lighter is particle, greater is the wavelength associated with. This shows matter waves are generated by the motion of particles. The waves are produced whether particles are charged particles or they uncharged. The velocity of matter waves depend upon the velocity of material of particle. That is, it is not a constant while the velocity of electromagnetic wave is constant. The velocity of matter waves is greater than the velocity of light. Smaller is the velocity of particle is greater than its wavelength. The wave and particle aspects of moving body can be never appear together in the same experiment. That's why we can say is that waves has particle like properties and particles have wave like properties, and the concepts are inseparably linked. Matter wave represented is a symbolic representation. The wave nature of matter introduces an uncertainty in the location of position of particle, because a wave cannot sit exactly at this point or exactly at that point. However, there is where the wave is large, there is good chance of finding particle, while where wave is small or weak, then there is a small chance of finding particles. Now we discuss about detection of matter waves, Davison and Germer's experiment, G.P. Thomson experiment, and Heisenberg uncertainty principle. Detection of matter waves. A wave associated with the motion of a material particle is known as matter wave, and matter waves are generated by both microscopic and macroscopic bodies. Before 1924, the electron was exclusively recorded as a particle, but after suggestion of de Broglie, the electron was given the wave-particle duality. There are many experiments and evidences which prove that electron is a particle and it has definite mass, charge, energy, and momentum. At the same time, there are some experimental evidences which prove that electron has wave nature and electron associated with the electron during its motion. Here are the following experiments: Davidson and Germer diffraction experiment, G.P. Thomson experiment. Now we discuss about Davidson Germer diffraction experiment. The first experimental evidence of the matter wave was given by two American physicists, Davidson and Germer, in 1927. The Faraday cylinder was removed on the circular scale, and for a accelerating V, scattering showed and peaking in a particular direction. With the electron beam incident perpendicular to the crystal surface, phenomenal scattering direction found to be 15 degrees for electron was accelerated to 54 volts. According to de Broglie wavelength, lambda is equals to 12.26 by square root of V. Here value is equals to 54. Then finally we get lambda is equals to 1.67 Armstrongs. From the X-rays analysis, it is note that a nickel crystal acts as plane diffraction grating with grating space d is equals to 0.909 into 10 power minus 10 meter. According to the experiment, we have diffracted electron beam at angle 50 degrees as shown in the figure. Thus Bragg's equation angle theta is equals to 180 minus 50 by 2. From the diagram, using Bragg's formula, 2d tan theta is equals to n lambda. By substituting all values, lambda will get 1.65 Armstrong. As the two values are in good agreement, hence confirms that de Broglie concept of matter waves. Now we discuss about G.P. Thomson experiment. G.P. Thomson performed experiments with accelerated from 1000 to 50,000 volts. In his experiment, he observed diffraction patterns exactly similar to X-rays patterns. Moreover, he was able to determine wavelength associated with electrons. Thomson experiment supports the concept of matter waves since the diffraction pattern is possible only if the waves are associated with material particle. Now, as we in the see the diagram, he taken one cathode and to pump air, it taken two holes, and he taken gold foil and a slit and photographic plate. After developing the plate and symmetrical pattern consisting of concentric rings about a central spot is obtained. This central spot is also applied in neutron rings also. This pattern is similar as produced by X-rays. Electron diffraction pattern with the gold foil. Observe this diagram. Finally, he get neutron concentric rings with a central spot. By this experiment, he can conclude that matter has Wave has both particle and wave nature. Matter waves have both particle and the observed ring. A shift in the electron beam directly observed with the applied magnetic field. It shows that pattern is produced by electrons and not by X-rays, as X-rays pattern is not affected by electrics and magnetic fields. The observed rings can be interpreted only by considering the diffraction pattern of the electron beam, which is due to gold or aluminum foil, as the diffraction pattern can only produced by waves, not by particles. Thomson concluded that electrons behave like waves. The following conclusions have been drawn from the experiment. Thomson experiment clearly demonstrated that existence of matter waves because diffraction pattern can be produced by waves. The calculated wavelengths obtained by the diffraction pattern agree well with the wavelengths obtained by the de Broglie's relation. Thomson calculated wavelength associated with the electrons with the help of diffraction rings. The associated wavelength depend upon the accelerating voltage and independent of material of the target, whether it is gold or aluminum. Now we discuss about Heisenberg uncertainty principle. It is exactly calculate it is very difficult to calculate the exact position and momentum of a particle simultaneously. The certainty was explained by the Werner Karl Heisenberg in 1927 through his Heisenberg uncertainty principle. Let us take examples of narrow and wide wave packets. In a narrow wave packet, the position of the particle can be preciously determined but not wavelength. As a result, particle wavelength cannot be measured accurately and there are not enough waves to exactly measure wavelength. Delta x is small and delta p is large. On the other hand, in a wider wave packet, the wavelength can be determined, but the position of the wave particle isn't determined. Delta x is large and delta p is small. Hence, it is conjectured that it is impossible to calculate the exact position and momentum of a particle at simultaneously. The Heisenberg uncertainty states that measure position and momentum of a particle at any accuracy is a very difficult process. In other words, the product of uncertainty is measured by the position, and uncertainty in the measurement of momentum is always constant and it is equals to Planck's constant. Delta p is the uncertainty momentum, and delta x is equals to uncertainty position is always equal to Planck's constant. It has been experimentally observed that product of uncertainties in position and momentum is equal to or greater than h by 4 pi, that is delta p into delta x is greater than or equal to h by 4 pi. Here is the total information about the quantum mechanics. Thank you for listening this seminar. Have you hope all of you enjoyed it.